Hey everybody, welcome to Parallel and Perpendicular lesson number 5. We get to do some actual math. This is sort of why they pay me. We've been going through a lot of definitions, a lot of frustrating stuff. It's really enjoyable to finally get to the point where we get to do some real math. Now, it's not going to seem that way at first. Give me a few minutes and you're going to see where there is actual math taking place. All right, so we're going to bring triangles into the picture today because we need to see how it relates to parallel lines, and I promise it does. So we're going to start with triangle names, which I think you've seen these before. We have scalene triangles, isosceles triangles, and equilateral triangles. Now, a scalene triangle has 3 random sides. None of them are the same length. They're just sort of out there. So none of those 3 side lengths are the same. They're just scalene, and that's just the way it goes. Isosceles would be if 2 of the sides are the same. I don't want to spoil it for you, but later we'll learn that if 2 of the sides are the same, then that means 2 of the angles will also be the same, but we don't need to get into that right now. And then we have equilateral triangles. Equilateral triangles are where you have each side the same. And just like we talked about with isosceles, how if you have 2 of the same side, you have 2 of the same angle. Here, with equilateral, if you have 3 of the same side, you actually also have 3 of the same angle, which means these are, weird word, just a heads up, equiangular. Not a very common word, but that's okay. Now, we have also already brought up the idea of acute, right, and obtuse triangles based on angles. So now we can classify triangles based on both angles and sides. So now you could say that this triangle is both equilateral and equiangular. Same side lengths, same angle measures. Again, that second word is not used very often, but that doesn't matter. Go with it. It's going to be something that we are going to use to classify. All right, now, this next one. The first thing I notice is that all the angles are less than 90 degrees. That is going to make it acute. And then if you look closely, you'll notice that all of the sides are different, which means it is scalene. So we have an acute scalene triangle. So this next one, we do have a right angle in here, but all the sides are different. So we're going to call it a right scalene triangle. And then last but not least, we have a very large 128 degree angle in there, which makes it obtuse. However, 2 of the sides happen to be the same, so we're not going to call it scalene. We are going to call it isosceles. All right. Now this is where the actual math comes in. Again, this makes me happy because that's what I'm here for. We get to deal with the Triangle Angle-Sum Theorem, which is short and sweet. It says the sum of the measures of the angles in a triangle is 180 degrees. All right, now, we are in the middle of the parallel and perpendicular chapter. So it's natural to just have the simple question, what does this have to do with parallel lines? I'm going to prove it to you. So I'm going to show you 2 parallel lines. I'm going to show you why this idea relates to parallel lines. Okay, so we're going to draw a triangle here. And we're going to go, we'll do that, and then we'll make this one maybe just a little bit wider right here. All right, and these lines are parallel lines, so I'm going to mark them that way. I'm going to do that and that. Okay, so let's just say, off the top of our head, that this right here is 70 degrees. We've got a 70-degree angle right there. Well, if that is a 70-degree angle, and we were to swing back down to the other alternate interior angle, we know that all alternate interior angles are congruent, which means if we had 70 on the upper left, we are going to have 70 down here. All right, so let's say we've got a 55-degree angle right here. Well, again, that means the other alternate interior angle is going to be 55 degrees. Now, if you look up here, those three angles together should add up to 180 because these three angles put together make a straight angle. They make a straight line. So whatever is left over from 180 should go right in this spot. So 70 and 55 means you end up with another 55-degree angle right there, because those three numbers would add up to 180. Now look inside the triangle. We still have a 70 and we have two 55s, just like we had on the outside here. And since we know this has to add up to 180 and all of these angles match, that means whatever is inside the triangle also has to add up to 180. And it doesn't matter what numbers we used here. You know, this angle right here could have been called 78. This angle right here could have been called 61. It doesn't matter, because the same three numbers that we put here, here, and here that have to add up to 180 are also going to appear here, here, and here. There's no way around it. All right, so even though it doesn't necessarily seem like it's going to be related, it is. Let's go to the second theorem today. There are only two, and this would be the Triangle Exterior Angle Theorem. And full disclosure, I don't use this one a lot because usually I can find a way around it that makes more sense. But for some of you who are definitely into the theorems or into memorizing things, I think it'll be helpful. The measure of each exterior angle equals the sum of the measures of its two remote interior angles. I'm running out of room just a little bit. You can work with it. Now, the word remote means far away. You use a remote control if you are far away from the TV. So when you see the picture, I think it'll probably make more sense. So what I'm going to do, I'm going to put a triangle right here. There you go. We'll just do a ray right here. Looks good. All right. The measure of each exterior angle. An exterior angle is what you get when you take the side of a triangle and then you just continue it past the triangle itself. So instead of stopping right here, you keep going. That would be an exterior angle, which I'll just mark 1. Okay. Now, a remote interior angle, remember remote means far away, so that would be the angles that are far away. So that would be here and here. This right here would not count as a remote angle because it is not far away from angle 1. Okay. So let's break down what this means to us here. Let's take these two theorems and actually write it out. So the way it's listed in the book, which I know you're totally enthralled about, this first theorem right here, the Triangle Angle-Sum Theorem, says that the measure of angle A plus the measure of angle B plus the measure of angle C equals 180. I think we could pick up on that. That doesn't seem like a terribly big deal. This second one, the measure of each exterior angle. So the exterior angle in this picture would be angle 1, equals the sum of the measures of the two remote interior angles. So that would be angles 2 and 3. So that would be angle 1 equals the sum of 2 and 3. Okay, let's do a few examples here. Let's just solve for x, see where we go. Let's start with this one. We have 65 plus 57 plus x, and we want it to equal 180 total. Doesn't seem too complicated. We have 122 plus x equals 180. Basically, we're just subtracting to see what's left from our 180 so that we can solve. So x equals 58 degrees. You add up 65 and 57 and 58, you end up getting 180. The next example is actually pretty easy because we have 90 utilized by a right angle, which means we only have 90 left. I'm not going to set up the equation because if you have 90 to spend and you have spent 40, you now have 50 left. So x equals 50 degrees. All right. Now, this next one, it looks like it would maybe be an example of the exterior angle theorem, but it is not because this angle is not actually an exterior angle. Remember, an exterior angle is what you get when you continue one side longer. Here, we actually continued both sides longer, which creates a vertical angle instead. So if we can figure out what this is right here, then that means x will be the same thing because they are vertical angles. 30 plus 20 is 50. That means the leftover would be 130 degrees, which makes sense. That is a pretty big angle right there. And then since x would be vertical to that, that means here x would also have to be 130 degrees. All right, the fourth one. I think this would be best to set up in an equation just so we don't forget. And we are going to say 70 plus 60 plus 8x plus 2 equals 180. So the part plus the part plus the part equals the whole thing. And that's going to give us 8x plus 132 equals 180 because I'm going to combine all of the like terms. Then we're going to subtract 132 from both sides, so that 8x equals 48. Seems like a lot of work, but we just figured out that x equals 6. Okay. All right. Last but not least, we've got this one right here, our last problem of the video. Now, our idea isn't going to work all that well as it is unless we can figure out this angle right here. The good news is we have a straight line. 137 plus whatever goes here has to be 180 because it would make a straight line. So you take your 180 and you take away 137 and you find out that we have 43 degrees right there. Now, this is where you could either keep going inside the triangle or you could use the exterior angle theorem. That theorem says that whatever this is will be the sum of the remote interior angles, and 102 plus 43 equals 145. Now, what would happen if you forgot the exterior angles theorem and you did not know that it existed? Well, you would figure out what's left from 180. 43 plus 102 is 145. Take that away from 180, and you would get 35 degrees. And then you would make a linear pair out of these two and figure out what was left from 180. You would still get 145 as your final answer. It might just take you an extra step. All right, hope this helps. Thanks for joining me, and I'll see you next time.